Hi, welcome to this video. We are looking at question number 8, right? Question number 8 of the FAMS sample questions. Okay, we have looked at quite a few questions already. We're just continuing. And this is number 8. Let's read the question. You are given the following information about a commercial auto liability book of business. And let's look at what else is mentioned in the question. Each insured's claim amount, each insured's claim count, okay, claim count has a Poisson distribution with mean lambda, where lambda has a gamma distribution with alpha 1.5 and theta is 0.2. So here in part 1 here, we are told that the claim count is Poisson with mean lambda, and lambda is gamma with alpha 1.5 and theta 0.2. So we know we are dealing with a mixing distribution now. Okay, begin connect, right? Even before we look at the rest of the question, we have got n, which is Poisson with mean lambda, and lambda is gamma. So you know that the unconditional, okay, unconditional, yeah, the unconditional distribution of n will be what? Will be negative binomial. Good. Okay. R will be equals to alpha, which is 1.5, and beta will be equals to theta, which is 0.2. Okay. So the unconditional distribution of n will be negative binomial with R equals to 1.5 and beta equals to 0.2. Okay. Then part 2 of the information in the question, individual claim size amounts are independent and exponentially distributed. Okay, with exponentially distributed with mean 5,000. Okay, great. So we know the expected value is 5,000. The mean is 5,000 and the variance, okay, will be 5,000 squared. Okay, great. The full credibility standard is for the important words for aggregate losses to be within 5% of the, expected with probability of 0.9. So this can help us with our lambda naught straight away, which will be YP over R whole thing squared. This is 90%. So your YP here is 1.645. And this R here is from here, which is 0.05. Okay. As we go through the information in the question, I'm just telling you the things that we need. Now let's look at the question itself. Calculate the expected number of claims required for full credibility using limited fluctuated credibility. Yeah, limited fluctuated credibility. So we are looking at aggregate losses here. So I just made some points there, right, in my handwriting. We're looking at a mixing distribution, and I've also mentioned that n is negative binomial now with parameters r 1.5 and theta and beta is 0.2. Okay, great. So first off, let's go ahead and work out the stuff that we need, the expected value of n. Let me move the screen up so that we can talk about it without any interference. Okay, remember what we're trying to find, okay? We're trying to find the expected number of claims required for full credibility, right? Using limited fluctuation credibility. So I have gone ahead and worked out all the information that I need. So let's clear this. So the expected value of n, because now we know it's negative binomial, will be R beta. Okay, R is 1.5 and beta is 0.2. You can get this value here. These numbers you can get on your own, right? I'm not going to talk about it. The variance of n, you know, is R beta times 1 plus beta. Okay, so plug the numbers in and you'll get 0.36. And I've also shown you the expected value of x because I'm told the claim amounts are exponential. So the expected value is 5,000 and the variance is good 5,000 squared. So lambda naught, I told you how to get it just now. We have got YP over R whole thing squared. You'll get this number. So some of us have memorized this number 1082. If you know it, just go ahead and use it, right? But I'm just trying to make this complete. So from the time we talked about, you know, our the number of claims that we need for full credibility and so on. I reminded you of this formula at that time in class. Remember this? Yeah. Okay. We talked about this. How we get to this formula, maybe we can talk about it in another video, but I'm just trying to solve the problem as quickly as I can. So we'll use n is bigger than or equals to lambda naught. And then I have my coefficient of variation, okay? Coefficient of variation for x, whole thing squared over expected value of n plus the coefficient of variation for n, whole thing squared, right? This basically, we derived it in our class, so I'm just going to go ahead and use it. Then you just plug in all the things that we have. Lambda naught we have. The coefficient of variation squared we have. That'll be sigma squared over mu squared. We've got the variance over your mu squared. And then this is the expected value of n, which is 0.3. And then this is your variance sigma squared of n over mu squared of n. The variance we had just now was 0.36. There you go. And then your mu squared will be 0.3 squared. You plug the number into your you plug all these numbers into your calculator, and you'll get n bigger than or equals to 7937 7937.6733 or something like that, right? Okay, 793. Let me just say 7938. Okay, 7937.6733. So we have expected value of n, right? We have expected value of n, which is 0.3. So per exposure, we have 0.3 claims. Okay, per exposure, we have 0.3 claims. So we have got 7937.6733. So you just take that. Let me clear this. Okay, good. So we have this number here, and we have the expected value of n, which is 0.3. So it's 0.3 claims per exposure. So take that 0.3 multiplied by your 7937 point something, whatever, you will get 2381.302. And we are done. Correct response B. Thank you very much for watching.